All right, in the last video, I implemented a dead simple data structure for orthogonal range search. And all it did was store the points and it just looped over the points to see which ones were in the input box. This time we're going to do something a little more clever. We're going to use a Kd tree. We're going to implement the Kd tree. So I described the theory of Kd trees in lecture, and now in the video, I'm going to implement them. So let's do that. All right, so here's my Kd tree. There's two things I need to do. Right, I need to build the Kd tree. So I'm going to take the endpoints and actually construct the Kd tree. And the second thing is I'm going to search the Kd tree. So I'm going to implement the range search. Now, it's a tree. It's actually a binary tree. It's a kind of binary tree. And so it's very natural to express both of these operations recursively. We could talk a little bit more at some point whether that's the best way to do this, but it's certainly, I think, the easiest, or at least the shortest, depending on how, I won't say easiest, it depends on how comfortable you are thinking about recursion. To initialize the Kd tree, to build it, I just get the set of points. And I know I'm going to try to make a left subtree and a right subtree. So from the set of points, I'm going to split it in half. I need to find the median. There are a lot of clever ways of finding a median, but let's not do any premature optimization. Let's just sort the points. And then once I sort the points, I'll just take the middle element. And so I want to sort them by their x coordinate. So I'm going to have to tell it how to sort the points. So I'll pass a key function, and I'll just write a lambda expression here that's going to take x, a point x, and return its first coordinate. And this will sort them by that first coordinate. And now I kind of know that I want to take that list now and split it into two halves. The first half will be everything up to m, and the second half will be everything after m. All right, and then I want to take these two halves. I want to build two new Kd trees, one for each half. One will be the left tree, and one will be the right tree. And of course, at first, this is not going to be correct, so bear with me. But if I just take this and just build the Kd tree on that half of the points, and I build the Kd tree on this half of the points. Well, I did build two smaller Kd trees. What could go wrong? Is it a little bit weird? There's always red flags when you have a recursive function that has no base case. You might think that the base case would be 0 points, but actually I kind of don't want nodes in the Kd tree with 0 points. And I would actually want to check to make sure there's some points here. So how would I check that? First of all, on the left side, m has to be greater than 0. So if m is greater than 0, I'll build the tree on the left. And what's the right side? Oh, I didn't say what m is. I just wrote m boldly. It doesn't mean anything. So let's write this down. N is going to be the length of the input set, and m is going to be n over 2. Sorry, I just boldly treated m as the median as if we had defined it that way, but now we really have defined it that way. It's at least it's the midpoint here, and so that'll give us the first half of the list. And the length of the second half is n minus m, and that also has to be non-empty. One of the handy things to remember about slices of lists is that the length of the slice is the end point minus the beginning point, because this is half open. Right? So this is the same as 0 to m. So m minus 0 is m. That's the length of this side. And this is the same as going m to n. So the length is n minus m. Okay, so is this good enough? Well, there's some obvious problems here. One of the big ones is that we never put the points anywhere in this thing. Where did the points go? There's two standard approaches here. One approach is to put everything in the leaves, right? So we do all the partitioning, and then all the points lie in the leaves in the end, which is good for a lot of things. It's maybe twice as big as it needs to be. So instead what I'm going to do is every time I split, I'm going to take that point that I split on, that median point, and I'm going to put that in the node, right? So that each KD tree object here, you could think of as the node, but it represents the entire subtree rooted at that node. So let's do that. Let's store that point. So p dot point is going to be, not p dot point, self dot point is going to be pm. All right. Now, if I've stored the point there, I don't need to store it in the subtree. And you'll notice that it's sort of in here. It's actually the first point on the right subtree. So I'm going to switch this to m plus 1, and I'm going to change this to minus m plus 1. So, all right, so this is looking pretty good. But there's another problem here. This will actually work in the sense that I think if we ran this code, we could probably build a KD tree. And it might even be the case that if you try to do a search, it might also work for search. But you probably noticed that every time I sort by just the first coordinate. So this x0 here, it probably should change. And if you think of the KD tree of each node having not just the point where it splits, but the direction or the axis or the dimension along which it's doing the split, we need to know that. Let's actually store that in there. There's a couple, we could try to do it implicitly, but I think it's nice to just pass it along. So let's say I pass along this d, it's d for direction or dimension, and the default value will be 0. And when we do this sorting, we'll just sort on that dimension. And after we do the sorting, we're going to have to pass the new direction down to the subtrees that we build. And the new direction will be the old direction plus 1 modulo the dimension, which we never actually put in here. You might think KD tree, someone should pass it k as one of the parameters. But if I pass it a point, I can just look at how long the point is, how many coordinates are in the point, and that should be good enough to tell me the dimension. Right? That is what is k in this. So I'll update d to be equal to d plus 1. Modulo the dimension, so length of, I guess we could just take P0. All right, so now when I make my recursive calls, I'll actually include this dimension. All right. I should try to make one just to check if this is remotely any good. Let's make a point set 1, 2, 3, 4, 5, 6. Here's my point set, and let's make a KD tree on that point set and run it. And it worked. Okay, it finished, and maybe that's good. Okay, so does this make sense? All we did was we just kept sorting the points, picking the midpoint, and then using slicing to take that list of points into 2 smaller lists and recursively build the next KD tree. And the only update was to change the direction. Okay, pretty straightforward here. Let's now do the range search. The input should just be a box. All right. And, oh, you know what I missed? I think that actually it's going to be useful when we do this search. Maybe I'll let it, if I think something's going to be useful, let's find out if it's actually useful. First, the search should do what? It should check, I think, to see if the point is in the box. I had that already implemented, this inbox function. Sounds like I'm talking about email, and actually I get a little triggered, kind of hate email. But let's bring that back. So this inbox function right here, and I think this simplest thing to do first is if self.point, oops, I'm gonna check inbox, self.point, and the box, I am going to yield self.point. Actually, I'm going to have to deal a lot with this point. I'm going to just make a local variable. It's just going to make my code just a little easier to read, I think. Okay, so if I do a range search and I start at the top of the tree, I check there's a point stored at that root, and I check if it's in the range or not. And then the naive first thing to try maybe is to then, after I check about that point, I can search the left tree, and then I can search the right tree. This maybe sounds like a bad thing to do, but it won't, at least won't be wrong, right? So it's not efficient because I'll end up searching the entire tree, but let's try it. So self.left.range search box. That will give me, what is that? It's going to give me a way to iterate over all of the points that are in the left subtree that are in the box. And what do I want? I want to yield them all. I could loop over them and yield each one, but I can also just yield from, which does the same thing. And I'll want to do the same thing on the right. All right, and this will not work yet. I'm pretty sure I'll get into trouble if I try to say store this KD tree and I do t dot range search on, it's a little bit ugly. Oh, I didn't import NumPy array. Let's bring in the NumPy array real quick just to do a really lame test. Just to do a test of something that I'm pretty sure won't work. I want to just give it a box. So okay, so wow, all right. That is just, that's me just forgetting to put some brackets around here. All right, and oh, it actually ran. It actually didn't give me any trouble with that. That makes me pretty uncomfortable. This probably should have given me an error. The reason I think it should have given me an error is because self.left and self.right might not even be defined. So that's weird. What should we do? How should we figure out that this code is really working? I could do what I did in the last video. We could just draw a bunch of pictures. I guess I could also just see what the heck it thought it was returning. Oops. I'm not sure I have enough parentheses here. Good. Okay, that time I did get an error. It says, I think maybe you can't see my whole errors. Oh, that's unfortunate. I got an attribute error. It says that there's no such thing as left. And that's kind of what I expected, because you can see at the base of the tree, if it doesn't hit, if m was 0, or n minus m plus 1 was 0, it doesn't actually make a left or a right subtree. So we could set them to none. Let's just do that. Okay, so they exist, but now what I'll get is a none type error. Okay, so I don't want to actually always go left or always go right. I only want to go left or right if I can. So if self.left is not none, I'll search the left, and if self.right is not none, then I can search on the right. So I won't get a none type error, and I think I can at least run this code. And I think actually it works. Okay, so it works. It doesn't mean it's good code, right? Again, if I search the left tree and I search the right tree, I haven't really gotten any improvement over just our linear proximity code. And the key algorithmic idea in thinking about the KD tree in terms of search, I think it's a little bit backwards from the way we think about search in binary search trees. So in binary search trees or other kinds of search algorithms like A** and these kind of searches, the goal seems to always be to figure out where you should go. Like, where should I go next? And in this KD tree, the improvement all comes from deciding where not to go. That is to say, how to prune off the search, right? So this botanical metaphor of trees and leaves, etc., gets extended when we talk about pruning off the search. And so you say, look, there's some direction. I don't need to search the left subtree because there's just no chance that the thing I'm looking for is going to be there. And so the way we see that or do that is the following. So I want to figure out where the split is, right? So there was some split. I'll give it a name. I'll call it the split. And the split was that dth coordinate of our point. Right, so the d is the direction of the current point. Oh, we don't know what d is. Oh, we don't know what d is. Were we supposed to keep track of d ourselves? We could, but really, I think we should store it in the tree. And notice we didn't store it here, so let's store it. Let's store it here. Okay, before we changed it. All right, so if we know the coordinate, that's where the split happens. And now, if I have a rectangle, and the upper bound on the rectangle is still left of the split, then there's no reason for me to search the right side. And similarly, if the left endpoint of the interval, as of the rectangle, if the rectangle or the box is a collection of intervals, right? There's one interval corresponding to the dth direction. If it's completely to one side, again, if it's completely to the right, then I don't need to search the left subtree. So I want to just add that in here. So, if there is something on the left, and I want to see if this split is less than something, right? If it's if it's greater than what? What is it? I guess it's that the box and the box, I want to know if it's greater than the minimum, which is this. This is a little bit hard to read. Let's do it like this. There's the split. I have the min and the max values for the interval. The dth direction of my range is just going to be box D. And so I wanted to make sure that this split is greater than or equal to the min. Right? That way I'll actually search the left side. And to search the right side, I need it to be the case that the split is less than or equal to the max. Okay. And so it could be that both of these hold and I search both sides, which is totally fine. It's just that sometimes one or the other or both might not hold, in which case, actually, I don't know if it'll ever happen that both don't hold. You could check me on that. But if one of these doesn't hold, then that's an entire subtree that we're not going to search, right? That's how we prune the search. Okay. And of course, I get an error. It says D is not defined because this is not D. It's self.d. Let's try this. Right. All right, so it at least ran. I don't know if I was supposed to get something in this. I think I was. It says I got no points. So, oh yeah, because 9, 9 is huge. Let's try this. All right, in this case, I got just the 0.34, which makes sense because that's the only one with an x-coordinate in the range from 3 to 4. All right, so I kind of believe that this works. This is a basic, straightforward implementation of a KD tree. What were the key ideas? We just used sorting to find the median. We stored the point and the current direction. We updated the direction. We had to use a little bit of modular arithmetic. And then we initialized the left and the right subtrees. And then if there were points on the left and the right after we did the split, we just made recursive calls to construct those subtrees. All right. The range search also turns out to be not too long. We take the point and we check if it's in the range. So every node of the KD tree stores a point, and so if we're visiting the node, we might as well check, is this point in the box? And if it is, we'll yield that one. And then we figure out the interval we care about from the box, right? That is the box interval in the direction self.d. And then we figure out where the point that splits this box, we look at its dth coordinate, and then we can use these two things, the min, the max, and the split, to prune the search. Right? And if we decide not to prune the search, then it's just a recursive call. And this yield from, again, you can think of this as just iterating and then yielding all of them. All right. What is tricky about this is analyzing it. You might think that the analysis is just a standard analysis, but it's one of the problems of being clever with your Python. This kind of generator-based tree traversal actually hides some complexity. It looks like it's just n log n, or I'm sorry, it just looks like a normal search, which if you work it out should be square root of n plus k. But secretly in here, there's another log n factor. But I'm going to let you think about this. So if you really understand what generators do, you can see why there's actually an extra log n factor. So if you were trying to optimize this, there's a couple like clear low-hanging fruit. One, I think, probably is replacing the sorting at every step with one of two things. One would be some fast median code, or pre-sorting all the lists by each dimension, and then when we split them, we can split all of them. I'm not sure that that's actually such a efficient thing to do, but it's often recommended. And then the second thing is obvious, a source of improvement would be to get rid of these recursive generators. And the way to do that is actually something that's common perhaps to do also with other algorithms that at first you want to implement them recursively, but then second you think better of it. For instance, things like depth first search in a graph in Python, you should not be implementing that recursively, even if you think about the algorithm recursively. And so you can take that recursion and instead just store an explicit stack and kind of use your own stack to manage all the calls that you need to make. And that would be an improvement here as well. So not just in terms of avoiding recursion errors from extreme recursion, which is not an issue here. You're probably not going to get a recursion error because you would need 2 to the 1,000 points. But you might get this extra log n factor from all the overhead of dealing with the recursive generators. So that's maybe a little bit esoteric, but I don't know, think about it. Think about how you improve over this. But for now, this gives us something at least that that seems to work, although we haven't written any tests yet. So maybe we'll see some tests and some pictures at some point.